As it turns out, we have different types of matrices, and it really depends on the type of values that are placed in there. So let's let A represent the matrix A11, A12, A1n, AM1, AM2, AMN. Okay. So there's different types based on the values that are assigned to the A's. The very first fundamental type of matrix is the idea of a symmetric matrix. And these are, a symmetric matrix is when all of the ij's are equal to all of the ji's. So in this case, the I represents the row. In this case, the j represents the row. So what that says is, if you have AII, by the way, or AJJ, that refers to the diagonal. What that says is, if I take the ith row and the jth column, okay, let's say that's here, AM1, and I go to A1M, not N, M, unless, of course, M is bigger than N. But in this case, suppose it's low, it's less. This is saying that this needs to equal that. So A11 needs to equal A11, A12 needs to equal A21, so on and so forth. So let's take an example. Let's just take a simple 2 by 2 matrix. This is symmetric. This is also symmetric. Okay, notice the diagonals don't need to be the same. It's just the quantities, right? This is A21, this is A12. They need to be equal. A11 is equal to itself, A22 is equal to itself. So therefore, by definition, it's a symmetric matrix. So look at another example. This is another symmetric matrix. A11 is equal to itself. A22 and A33 respectively are equal to themselves. But notice, A21 is the same as A12. A31 is the same as A13. A32 is the same as A32 is the same as A23. So notice that we have symmetry here against the diagonal. So put simply, a symmetric matrix is one where if I switch the rows and the columns, I get the same matrix. There's a nicer way to represent this, by the way. Remember the transpose operation. So we can actually say if A is a matrix and its transpose is equal to the same matrix we started with, then it's a symmetric matrix. And that should be obvious, right? Because when we take the transpose of the matrix, remember, we switch the row and the columns. That was from our discussion of a previous video we had. So for example, A3554, right? If I take the transpose of that, 3, 5 are the new rows for the first column, 5, 4 is the next one, and notice we just get the same matrix. If we do 1, 8, 4, 2, 3, 5, 3, 4, 8, and I take the transpose of that, again, this now becomes the first row, so I do 1, 8, and 4, right? 8, 2, and 3. Oops, 2. And 4, 3, and 5. So I construct that matrix from there. But notice I get the same exact matrix back. So therefore, by definition, it is symmetric. Now we have a few other matrices that we tend to focus on. we have not only we have not only symmetric matrices, but we have other matrices that are of interest to us that help us in some of our analysis, depending on what we're doing. So, for example, we may have a diagonal, which are big type of matrices, big in the sense that we use them quite often. So a diagonal matrix is a matrix such that Aij, for all I not equal to j, Aij is not, I'm sorry, Aij is equal to 0. If we have that, then we have what's called a diagonal matrix. Put differently, for the off-diagonal quantities, we have them set to 0. The on-diagonal parts of the matrix can be set to 0, but it can be set to other things. So, for example, this is an example of a diagonal matrix. Diagonal because the only non-zero quantities are on the diagonal. They can't occur on the off-diagonals by this restriction that we have here. This is another diagonal matrix, technically. We also have this one as a diagonal matrix, which is a very special type of matrix that we'll talk more about in a moment. So a diagonal matrix, put simply, the only non-zero quantities, if there are non-zero quantities, are on the diagonal. We also have what's called a scalar matrix. And a scalar matrix is a diagonal matrix where all the numbers on the diagonal are the same. Okay, so it doesn't matter how big the matrix is, so long as all the numbers on the diagonal are the same, we refer to that as a scalar matrix. So we basically say Aij is not equal, I'm sorry, is equal to 0 for all I not equal to j, and Aii is equal to some number, let's say c, some constant c, for all I. Okay, that's basically the definition of a scalar matrix. Now, we also have what's referred to as the identity matrix, which is also a very important matrix. The identity matrix is one where all of the diagonal, all the values on the diagonal they're just simply 1. And it's a very important matrix for reasons that will become very clear in a few moments. So an identity matrix is any matrix such that Aij is equal to 0 for all I that does not equal j, and Aii is equal to 1. So that's the identity matrix. By the way, there is this idea of a square matrix, which we work with quite frequently. The square matrix is one where the number of rows are equal to the number of columns, or I had used this as the number of rows. So moral of the story, the same number of rows as columns. And we work with square matrices quite frequently. Last, we have two very important types of matrices which help us do what's called decomposition, which we'll get to much later. We have what's called lower diagonal or triangular, and upper diagonal, also known as triangular. And what these simply mean is, for the lower, if we look at everything below the diagonal, we have non-zero entries in the matrix. Everything above the diagonal are just straight 0. So for the lower one, we know that if we know that the Aij is equal to 0 for all j bigger than I. Because notice that past the diagonal, you're at A12, and column 2 is bigger than the I. If you're at A22, right, then A2, 3, 4 are the quantities here. All right, so it's all the quantities past the row number, which must be set equal to 0. So you're going to have something like 0, 0, 0, 0, 0, 0, etc. And then you're going to have some numbers here that may be 0, may not be 0. Upper is the opposite of this. Upper is when Aij is equal to 0 for all j that's less than I. That's these quantities here, which will be set equal to 0. And these will have the non-zero entries. So let's look at an example of a lower triangular. Here we would have, let's say, something like 4, 0. That's upper because all of the quantities which are bigger than their respective row number are set equal to 0. On the flip side, we may have something like something like this. And this is upper triangular because the non-zero entries are above the diagonal, right? So that's the way we have to think about the matrices. Another way is that we can think that the diagonal will split the matrices up, and that is true. There is a factorization called the LU factorization, where basically we can write the matrix as a multiplication of two matrices between a lower diagonal and an upper diagonal. I'm not going to get into that this very second, because I haven't even discussed what does it mean to multiply two matrices together. Okay, but we will be getting into that in our future videos. But for now, I hope that you've gotten a pretty thorough breakdown of the different types of vectors and matrices. So again, summarize very quickly, two types of vectors. Okay, vectors are special types of matrices where they're either a 1 by n or an m by 1 matrix. Matrices can come in different forms. They can come in terms of them being square, scalar, diagonal, lower or upper, triangular, or as an identity. So we have a lot of different types of matrices. The reason why we need to know the types is because there are certain properties about these types that allow us to say some very interesting things about our systems of equations and more generally other things.